Hello everyone, welcome to the yet another seminar or the CERIAS seminar series. Today we have a speaker with us, one of our own colleague from Computer Science Department at Purdue, Professor Rajiv Khanna. He's an assistant professor in the department and he works on the areas of AI and also respectively they are like using optimization and other theoretical technique for AI. So without further ado, Rajiv.
Yes, thank you. My name is Rajiv, as Professor Kate mentioned. I've been here for a few years now. So this work it's called The Shape of Trust. It's built on optimization theory. It's at the intersection of optimization theory, learning theory, and interpretability, and you'll see how that comes about. Today's talk is actually an amalgamation of a few projects that my group has ongoing. So it's all based on joint works with brilliant students of mine. Gregory, who was here in Purdue CS, he's at LinkedIn now, and my current students, Vikai Chang, Haron Tang, and Yang Kim. So the idea here is that can we explore synergies in interpretability and optimization theory? So when we say why do certain algorithms work well or why do they fail, what properties of the data ensure that they will succeed in certain ways. So succeed in quotes here, I'll talk about what that means. So can we understand explicitly how different data distributions can impact loss landscapes and how we can leverage this for quote unquote better algorithms, and a couple of pitfalls along the way where there are certain limits to no matter what you do, there is a price that you have to pay. So there's like basically four things that I'll talk about the same time spent on each of them. So first, the theoretical framework of stability. I'll talk about machine unlearning. I'll talk about the core set problem, and then I'll talk about the pitfalls that I mentioned, which are the privacy risks in seeking better algorithms in some sense. So let me start with some very basic stuff. So you have some loss function that you want to optimize for to learn a large scale neural network model. It could be fine tuning a neural network. It could just be simple logistic regression, for example. So in general, you have a loss function L that you want to minimize with respect to the parameters W, and you want to find the best possible W star. Typically people use gradient descent for large scale models and large scale data sets. Using gradient descent is often not feasible, and there are other good reasons to use not gradient descent but do stochastic gradient descent, which is to say to set a certain hyperparameters which are eta and the batch size. So eta is a step size. So the idea here is to subsample a subset of the data in every iteration, in every sub iteration, and then based on the gradient of that subset, we update our current estimate of W. And we proceed basically like that. This is very similar to gradient descent, but there are quite a few differences that have been theoretically and empirically studied before also, and I'll talk about a few things today. So for example, there have been empirical studies that talk about stochastic gradient descent has sort of an implicit bias towards going to simpler functions or wider minima. And it has sort of this edge of stability behavior where the optimization trajectory follows along the line of something that is like barely stable. And then there are some empirical observations made on the spectra of the Hessian. So there is a certain structure that is implicitly it comes about in the Hessian spectra depending on what stage of optimization you are at. So how can we theoretically explain these observations based on data distribution? So that sort of like with that motivation, I'll jump into the very first sort of subtopic, which is local stability analysis. So the idea here is that yes, the loss landscape of neural networks is very, very complex. So something like on the left side. So what we are focusing here for the theoretical perspective of linear stability is that we look at the local properties around every local minima, and then we characterize under what conditions an optimization algorithm will quote unquote settle in the local minima or will it escape. So this is again the stochastic gradient descent equation. We assume certain simplifying sort of things which help us do and makes the analysis easier and more tractable essentially. I'll not go through the details, but essentially there are a few very reasonable simplifying assumptions. The most important one being that since we are focused on the local properties of the optima, we will assume that the local structure, the loss function, can be well approximated by a local Gaussian, a local second order approximation of the loss function. And based on that, we will analyze how do different algorithms, SGD versus other algorithms, settle into a local minima or they escape it. So this simplification sort of like comes at it brings us this sort of tractable way of looking at the update equation for the parameters W. It basically follows this linearized structure which is written here, and then we want to analyze when is this recurrence relation stable. So we let's say we have a Jacobian matrix J. So basically our iteration is W is equal to JW, right? And then under what properties of J, we are ensured that the norm of W will settle to be finite, or if it is unstable, will it go to infinity. So when we say it is unstable, that essentially means that eventually this recurrence relation will explode. So the norm of W will explode. Equivalently, it can be written as this bunch of Jacobians multiplied together. The two norm of this multiplication together as k goes to infinity, it will explode. So that is sort of the theoretical tool with which we are working. I don't expect people to understand like every nitty-gritty about like things here, but essentially the idea here is that we are looking at linearized dynamics of W around the local optima, and based on that we are trying to understand will the optimization algorithm settle in that local minima or will it escape. So for this purpose we will introduce a new coherence measure, which is essentially looking at how well are the Hessians of individual data points aligned. So the coherence measure can be defined as it is written on the slides. Again, my goal here is to put as much math as possible on the slides without it seeming too dense, just for clarity and for completeness, while I personally, like when I'm talking, I'll try to talk about more intuitive things. So this coherence measure essentially measures for any two data points I and j, how similar are their Hessians. So it is a metric that basically captures that similarity. So if there is a lot of misalignment amongst the Hessians of individual data points, for example, if they are all the Gram matrix, which is a similarity metric of that Hessians, is essentially diagonal, then this will be relatively bigger, for example. And then if it is not the case, then it will be smaller, right? So it is measuring how similar are individual data points, but not in the input space, in sort of this Hessian space, which intuitively you can think of it as the way that through the stability lens, the model sees the data points to be similar or dissimilar. That's the idea. So based on this, we are able to extend the standard gradient descent stability condition to something that is more general, to stochastic gradient descent. So here this is saying that the SGD algorithm will settle into a local minima that satisfies this condition, or in other words, explicitly what it is saying exactly is that if the largest eigenvalue of the Hessian is larger than a certain quantity, which depends on how well the data points are aligned, the Jacobian metric that I talked about, it will explode, which means that it will make the system unstable and the optimizer will not settle there. If this is not very clear, just give me a couple of slides and things will start becoming more intuitive. And similarly, so we have talked about SGD. So let's talk about another algorithm where instead of just minimizing the loss likelihood, the loss function, we are saying we won't do min L, we'll do min max, where min is over the W, which was the case earlier also, but we will also have this perturbations allowed. So we will be minimizing W over maximum possible perturbations you can make around every W. So what effectively this captures is that instead of letting SGD settle into any minima, this is saying we are going to explicitly hunt for minima which are wider or flatter. And because there is a lot of empirical evidence that says that those minima tend to generalize better. So now we want to analyze a variant of SGD, which is the cost function is this, but essentially intuitively it is saying I'm not just going to do SGD and let it settle wherever. I'm going to try to do something more clever, slightly more clever, and say that, hey, this is I'm going to hunt for wider minima explicitly. I mentioned that there is an implicit pull when you do SGD, and there is implicit sort of behavior that SGD tends to go to wider minima. But here we are explicitly modifying the cost function so as to make it, for the lack of a better word, more explicit, that W should not settle in the local minima where it is too sharp. So this we can apply the similar sort of linear stability behavior, and we get a slightly modified equation of when do things explode. So what this is together, this result and the previous result tells us that SGD will implicitly regularize towards minima where the Hessians are more aligned, and that translates to the case that Hessians are more aligned means that essentially the gradients are more aligned if certain additional conditions are met. So basically SGD will try to find minima which are simpler. It is implicitly trying to align the gradients more. It is trying to find isotropic minima. And SAM, even though it was explicitly designed to find wider minima, the way that it is implemented, it's first order approximation, because in general this is a very hard problem to solve. It finds minima which are even simpler than SGD. So it will escape from minima where SGD settles, because those minima are simple enough for SGD to settle in, but are not simple enough for SAM to settle in. So when I say SAM, I mean sharpness aware minimization. So by seeking wider minima, we are implicitly also seeking more isotropic minima, where even though there might be the data distribution might be very weird, the algorithm is going to try to align the gradients implicitly and find W that achieves that perspective, that achieves that goal. So there will be many minima in which SGD might settle in, but the gradients are not, or the Hessians are not aligned enough for SAM to settle in. So in other words, seeking wider minima implicitly regularizes the optimizer to seek more isotropic, more aligned, more simpler minima in some sense. So this is like the theoretical sort of motivation, but is it just theory or can we actually check this in practice? So for that, let's take a small detour into interpretability. Now the instance attribution interpretability question is that given a bunch of training data, given a black box model that I only have access to the gradient of, and some test data points, can I figure out what training data points were quote unquote most responsible for making predictions on certain points of interest in the test data. So in other words, if it's an image of a dog, it was predicted as a horse, what training data points did the model rely on to make that misprediction? Or even if it is predicted correctly, what training data points did the model rely on to ensure that it makes that certain prediction on that certain test data point that we are considering? So to test our theory, we want to see how well it translates to real world scenarios. What we do is that we calculate these influences. We explicitly can take out data points from the training data and see how the prediction changes on given test data points, and that can help us capture how much is a certain training data point influential on a certain test data point. And then based on that, we define this entropy metric, which is essentially measuring that for a given test data point, how well is the influencing training data points in the training data spread out. So for example, if you have, let's say, an image of there's a class called tigers, and then there are the class has many yellow tigers. Now the entropy of a given yellow tiger in the test data set will be spread out a lot, because there's many yellow tigers in the training data. On the other hand, there's a white tiger which is very like a much less frequent. That white tiger is influenced by other white tigers in the training data, and so since it is influenced by fewer data points, the entropy spread is lower, right? So that is the concrete example. So basically, you can try to characterize the data distribution using this typicality score kind of a metric, which says that, for example, if the entropy that I just defined is low, which means very few data points in the training data influence a given test data point, that's for example an image of a white tiger, then that data point is more atypical. And if it is influenced by many data points in the training data, then that data point is more typical. Like there's many more typical white yellow tigers than there are a few atypical white tigers. And this can extend to further other cases where maybe there is an image of a tiger with an elephant, but it is labeled as a tiger. So it can be very confusing for the model. And that will be an example of something that is even more atypical. So the entropy there will be even lower. So what we do here is that we calculate this atypicality score that's on the x-axis, and we bucket this, and we see that how does the width of the minima that we calculated in the beginning of this talk, how do different algorithms behave in terms of generalization performance on different atypicality scores. So in other words, how does the loss landscape sort of interact with data distribution, how long the tail is of the data distribution to sort of define generalization performance on unseen test data. So here, for example, as we see that if you go towards the right hand side on this x-axis, that's where more yellow tigers are. So that's more typical data points. So there the width of the minima does not matter as much. So there you will see that SGD and SAM both behave similarly, but as you start going towards the left side, as you look at more and more atypical white tigerish kind of data points, you will see that the generalization accuracy gap tends to become larger and larger. And in fact, most of the gain that comes from that comes in using SAM actually comes from more atypical data points. So there have been empirical observations made by other people, like on huge data sets altogether, that SAM or wider minima algorithms in general tend to do better. But here we are looking at it through like a finer grained lens in terms of how typical or atypical the data distribution is. So this also tells us that the major gain in wider minima is coming from this better alignment of the yellow tigers with the white tigers. So for SGD, it turns out that because there is less alignment, yellow tigers will predict more on yellow tigers, white tigers will predict more on white tigers. But here, because of this more entanglement, you will see that more yellow tigers, more common features tend to be used for predicting on both the subclasses. And this is also if we try to visualize the loss landscape. So for example, if we only look at low memorization data points or high memorization data points, so we'll see that if we remove all the white tigers from the data and we just run SGD, SAM is actually not even required. It implicitly pulls you towards wider minima. But as you start throwing in more and more atypical data points, the minima becomes sharper. And that's where SGD sort of like starts failing, because it's not able to generalize better on these rarer sort of data points. And SAM, because it hunts for more isotropic minima more, it will generalize better on these longer tail data sets. And many of the practical data sets are longer tail, right? So with that, let me come to the second part of the talk, which is machine unlearning. So the idea of machine unlearning is that there is a forget set. So there is a bunch of data points that form the forget set, and there is a bunch of data points that form the retain set. So a model has already been trained. So our goal is to sort of fine tune the model. So without having to retrain the model, can we try to do something where the performance on the retain set is not changed by much, but the performance on the forget set becomes bad. So we want to forget basically that the model knows anything about the forget set data points and retain as much as information as possible, which translates to higher generalization accuracy on the retain set. So obviously there is this sort of interference issues that come about, and because of that, if you just do something simple like, for example, this cost function where you will minimize the loss on the retain set and then minimize the negative loss on the forget set and try to balance the two with some hyperparameter alpha, that there is an algorithm called negative gradient that does that. But they basically, it's an empirical paper where they say, okay, this is what we do, it works reasonably well, but we'll try to use the insights developed in the first part of the talk to see if we can do something better. And this again, we are able to extend the linear stability theory that I talked about in the beginning, and we say that for this cost function, yes, we can give first convergence guarantees, and SAM's test error accuracy is better, but mostly because SAM has this inherent sort of alignment properties that ensures that even for rarer classes, they tend to align amongst each other better, which basically says that if there are more noise directions in the loss landscape, the wider minima isotropy tends to ignore that. But this property it works for the standard machine learning problem. If you are trying to do this minus like plus on the retain set and minus loss on the forget set, there the SAM denoising property sort of like shuts down. So that's a theoretical result, but essentially this says that we cannot just blindly apply, instead of using SGD here, if we try to blindly apply SAM here, it will not work. So what we are going to do here is that we'll ask a slightly harder question. Can we, the question is still similar, but like more like flavored towards machine unlearning, which is saying that can relative interactions of like loss landscape and data distribution help us design algorithms for machine unlearning. So the idea here is that we'll do something, instead of hunting for wider minima, which SAM does, we will hunt for sharper minima. We define a new algorithm. We call it sharp SGD. Instead of sharpness aware minimization hunting for wider minima, we'll modify the cost function and run sharp SGD, but with a twist that we'll do SAM on the retain part R and we'll do sharp SGD on the forget set, with the goal that we intentionally want to overfit the forget data set so that it can be easily forgotten. And another sort of part of this is that we will split the whole big parameter space, millions of parameters possibly, by trying to figure out which part is contributing more towards the retain part and which part is contributing more towards the forget part. And that essentially is the algorithm. We test it across many different data sets, many different baseline algorithms, and we find that consistently this proposed algorithm where you are running sharpness aware wider minima seeking behavior on the retain set and sharper minima seeking behavior on the forget set tends to prove better, and with theoretical foundation and empirical successes also. And these are some of the results. There are more results in the paper. I'm happy to share the paper. The paper is on arXiv already. We submitted it to ICLR. We're hoping for a positive result, but we'll see how that goes. Yes. So with that, let me talk about another application, again with the goal of can these theoretical insights developed using the stability behavior help us design better algorithms. So we've designed one better algorithm than all the other known baselines on machine unlearning. Now let's focus on the core set problem, which is basically the data efficiency problem. So instead of calculating the gradient on, when we are doing stochastic gradient descent on the full data, we are going to try to figure out if in each iteration we can find a subset of data points. If we calculate the gradient on those will be effectively as good. So now there is a trade-off in terms of how do we hunt for these a few data points, And if that Hunt optimization problem is itself more costly than just calculating the full gradient, then obviously it is not worth it. But there are several optimization algorithms proposed which tend to do just that. They will try to find a subset so that the total gradient of the subset matches closely with the total gradient of the full data set. And they will use just that subset in that particular iteration of gradient descent. But the problem here is, again, from the insights that we derived in the beginning, it tends to make the system more unstable, because intuitively, if you see, we want to go in a certain direction on the loss landscape, because we are selecting few points, generally about, let's say, 10% of the whole data. We might point in some direction which is inherently very dissimilar from where we actually want to go. And there is some noise already built in the stochastic gradient descent, but eventually it will go in the right direction. But now we are saying we are adding sort of like more noise in the stochastic gradient process, and we are saying we are only going to use gradients of just about, let's say, 10% of the data or 5% of the data, and then try to do the optimization faster, but by how much do we pay? But essentially what happens because of this is that because you are using way fewer data points, you are essentially introducing more instability, more noise in the data, which means that your optimization trajectory may start to deviate from what it would have been if you had used the full gradients. And that, if you try to plot the loss landscape surfaces, it means that there are more points of jaggedness on the loss landscapes. So this is for a simple MNIST data, two-layer neural network. So on the right hand side is the actual loss landscape if you use the full gradient descent, and on the left hand side is the induced loss landscape if you use, let's say, 10% of the data. So this is saying because of this additional noise introduced at any given point in the trajectory in the optimization process, because you can shoot off in arbitrary directions, that is equivalent to saying I'm going to add certain points of instability or certain points of non-smoothness in the loss landscape. And because of that, your performance may suffer. It is especially bad if your labeled data set is noisy, which means that if you have several data points which were actually dogs but they were labeled as horses, the classic core set problems. There's a bunch of papers on this. I think maybe like 15-20 papers I can think of, like on the top of my head, which employ some variation of this technique, and all of them actually perform fairly bad when there is noise in the labels, right? So how do we fix this problem? So we do something called Bayesian posterior sampling, which is to say that instead of just like SAM, again deriving on the insights of stability theory in the first part, just like sharpness aware minimization tends to solve this min-max problem, we are going to say that we are not just going to try to estimate the closeness of the gradient, we are going to try to estimate the closeness of the gradient with some epsilon brawl around the W, right? And then we want to minimize the effective sort of cost function, which is expectation under some distribution of W. Instead of just saying at a given W, I'm going to try to closely match the full gradient with a subset of the gradient, right? And we tried a bunch of different distributions to see which one works best. So for example, maybe you might think that using Hessians might work best, but approximating Hessians on large scale is fairly costly, and most practical methods will tend to do some sort of approximation, and that approximation itself is enough for the Hessian metric to perform not as well as just doing a simple normal distribution with some hyperparameter sigma noise added in every iteration as you are doing this subset sampling. There are some theoretical results also. So essentially what this theoretical result says that whatever misalignment happens because of choosing certain subsets in the classical core set selection problem, that does not happen anymore now under some fairly reasonable assumptions being made. And not just that, the error in the gradients is also is smaller, but also you can think of it as even the second order information can be more closely matched if we try to do these small injections of noise using Bayesian posterior smoothing around the local optima every time we are trying to do subset selection. So this gives much better performance, especially in noisy label conditions. So for example, we show that we can speed up the training on ImageNet 1K up to 3 times with no loss in generalization performance. There is a significant reduction in memory footprint versus, let's say, the largest, if you try to use the best second order approximation method out there. And especially, like I mentioned, in context of noisy labels, if 50% of the labels are corrupted in the training data, then our method is at least 7% better than other methods on ImageNet 1K, that other baseline methods that exist. So this is 7% not relative, it's actually absolute, which means that if the other method is performing at, like, let's say 60% accuracy, ours is performing at 67% accuracy. Some graphs here. So on a bunch of different data sets, what is the accuracy? On x-axis is the number of iterations, on the y-axis is test accuracy, so out of sample accuracy. The orange one is something called CREST, which is the previous state of the art second order costly method, and the blue line is ours. So you see that we achieve the same accuracy much faster in the training process, right? Yeah, actually, for this is non-labeled, non-noisy data. For noisy data, even the final accuracy that you arrive at is also better, like I mentioned. Great. So with that, let me come to the last part of the talk, which is, so we have talked about how the stability theory can help us recognize why certain algorithms can do better through this alignment properties of Hessians and gradients. And then we have talked about 2 scenarios where these insights can help us design better, faster algorithms, not for just machine learning, but also machine unlearning. But now we'll say, like I mentioned in the beginning, there might be some pitfalls. So this is more of like a no free lunch sort of idea, where just seeking wider minima in general is not always better. So we'll specifically see how there might be more privacy leakage. The intuition is simple. The intuition is that because wider minima tends to do better on smaller, rarer subclasses, effectively the relative importance of those rarer subclasses is enhanced, is increased. And because of that, there is more information retained about those rarer subclasses within the model itself. So it's not memorization per se, where memorization is generally in the literature right now, it is defined as a certain data point is almost exactly copied into the model. So instead of learning some structure where it is learning some common properties with other data points, it is essentially being copy pasted into the model itself. But instead of doing that, there is a form of structured memorization where a subclass like white tigers is learned, is memorized more, which leads to more privacy leakage. So for that, let's look at something called membership inference attacks. So the goal of membership inference attack is, can we sort of look at a model and try to reverse engineer what data was used to actually train that model. So in context of, let's say, medical data, if there is a diagnostic tool, it can essentially means that if the attacker's advantage is high, or in other words, given a data point, if an attacker can accurately identify whether that data point was actually used to train the training data or not, that would essentially mean that it can figure out whether a given patient has a certain condition or not, right? So the setup is as follows. There is some model. So depending on the setup, there are different levels of access granted to the adversary. So here for us, we are only looking at sort of like a black box access to the model. So the attacker can input a data point into the model and will get the prediction made on the model on the outside, right? That there was some training data that was used to train the model. The adversary doesn't know that, but can the adversary figure out for a given data point whether that was actually part of the member training data? Was that data point was actually a member of the training data set or not, right? So for that, we'll look at something called mutual information. So if not, maybe many people might have already seen this before, but mutual information between two random variables essentially quantifies the amount of information one random variable has regarding the other one. So it's basically looking at the expected value under the joint of the joint, the log joint versus the log marginals, multiplication of the marginals. So of course, for example, if two variables are just independent, then the numerator here will be exactly equal to the denominator, and then log 1. So it will have log 1 there, and then the mutual information will be 0. So if two variables are independent, mutual information between them is 0. But if they are not independent, then the sort of log differences in the joint versus their individual multiplication of marginals will sort of define as a metric to capture how related they are, right? So intuitively, if there is a lot more captured into the W, so if you can think of the W, the parameter of the model, as sort of a random variable defined because it is learned through a random optimization process, right? So if you think of it as a random variable and you think of the data set being drawn from some random distribution, you can think of the data set as a random variable. Then the mutual information, the more the mutual information between the model and the data, the higher basically is the chance, the attacker advantage that it will be, the attacker, he or she will be able to figure out whether a given data point was actually used to train the model or not, right? So that brings me to this new result we have that basically says that if you train a model using SGD versus if you train a model with like specifically more wider minima seeking behavior, you will learn a model where the lower bound of the mutual information between the model and the data will be bigger than will be bigger for SAM than it is for SGD. So in other words, if X is the minimum amount of mutual information between a model and the data set for SGD, Y is the same quantity for SAM, then SAM is bigger than Y is bigger than X essentially. And this translates to higher attacker advantage also. So intuitively that will come about because since there is more alignment of different Hessians or different gradients for smaller subclasses. For SAM specifically, it happens in a subspace that is because of over-parameterization that is somewhat orthogonal to the overall subspace of the entire model. And because of that, you in that smaller subspace where these interactions amongst white tigers is more, you can figure out with higher confidence whether a certain white tiger was actually used to train the model or not, right? So another way of empirically checking this is we look at memorization scores explicitly. So this is for a CFAR 100 data set. So explicitly what we did is that we looked at for the CFAR 100 data set, we randomly removed some data points from the training data and we retrained the model and we checked how does the prediction change on that same test training data point which was removed. So if there was a lot of change, that means the memorization score of that data point is higher, which means that that is a more rarer class. So that's more white tigers, as opposed to if there are many yellow tigers in the data, we don't expect the prediction on a particular yellow tigers to change, because there are many other yellow tigers which will ensure that the prediction on this current yellow tiger stays about the same. So then what we do is we plot the memorization scores for on x-axis we have for SGD, for y-axis we have SAM, and we see that and we try to do sort of a ridge interpolation. So basically what this graph is saying is that memorization scores, especially for structured memorization classes, so not too rare but not too common also, so sort of like a bunch of white tigers, maybe not white tigers which are labeled as horses, but white tigers and white tigers like maybe with other animals or tigers behind trees. So for those kinds of data points, there is more structured memorization. The memorization scores are on average larger for that bucket of the data, and those buckets are essentially exactly what are responsible for more privacy leakage, right? And then these are some of the data, some empirical results on explicitly checking membership attack scores, and here also across many different data sets we see that it actually does better. The membership attack accuracy or membership advantage for the adversary is more for SAM, for wider minima seeking behavior, than the other way around, than for SGD. So there are some other applications of like how we can use the shape of the loss landscape and how it interacts with the data distribution to try to figure out how we can design other algorithms. So for example, something that my group has also explored is in context of active learning and data summarization. So if you want to only retain the best possible performance on the test data while also compressing the training data the most possible, then the 80-20 kind of thing to do here is that you chop off the tail. So you might pay by higher worst case accuracy on the smaller groups, but if your goal is to retain as much generalization accuracy on test data as possible using the minimal amount of training data, the obvious thing here is to use the loss landscape differential between the two algorithms to act as a proxy for how typical or how atypical a data point is, and then use that metric to chop off the tail to only retain typical data points as your summary and use that for further downstream tasks, because that is the chunk that will give you the largest accuracy on the test data. And similarly, we have a similar setups on active learning setups, especially for out of class active learning, which is again saying that because of this differential in alignment of Hessians and gradients, we design algorithms that for a new data point, for an unexplored sort of area of the feature space, if we add a new data point, how atypical that will be with respect to the training data that we already have. So instead of using classical measures like entropy, we go one step further ahead, because entropy fails in certain scenarios. We go one step further ahead and say that we are looking at how atypical a new addition to the model will be with respect to the data that we already have. And then we add more atypical data points, because that increases sort of the information capacity the most while we are building the model using active learning. Right. There are many open questions that my group is exploring. Many of them are theoretical questions, like is there a limit to compression? So for example, what are the theoretical limits of machine unlearning? Can we say that if there are certain properties of the data, if the feature distribution is such that white tigers and yellow tigers are very close, then there is a limit to how much you can unlearn, even if you are unlearning only white tigers and not yellow tigers. right? So the trade-off between how well you do on the data that is being retained versus how much you are willing to forget on the forget set, that trade-off itself, there are many theoretical questions that that still we are exploring to see, let's say through the lens of mutual information between the two, and see what that defines as the limits of machine learning. That up to a certain point, we cannot do better than a certain quantity, a certain amount on the retain set without paying something on the forget accuracy also. Great. So yeah, there's many other problems also. So for example, SAM is trying to seek wider minima, and the way that it is implemented using this first order approximation, that is the algorithm that leads to alignment of gradients and Hessians. So the very important underlying question here would be, is it actually the wider minima that we seek, or is it actually the isotropy in the minima that we seek that implicitly comes about? And if that is the case, if it is the isotropy we seek, why not design an algorithm that explicitly seeks the isotropy? So earlier SGD implicitly we saw is going towards wider minima, and then we designed an algorithm that explicitly does that. And now I'm saying that it is actually isotropy that this wider minima seeking behavior is achieving. Then why not design an algorithm that explicitly does that? So that is Young, one of my students is working on that. And there are other open problems also, like if any of the students are interested in exploring, especially in the context of limits of the learning and privacy trade-offs and the limits of machine learning, we'll be happy to chat more. So with that, I'll stop. I think I well within time. Yes. Okay. Thank you. Great. Are there any questions?
Let's first thank the speaker. Okay.
Professor Khanna, my name is Swastik. Sorry I came in late, by the way. Had a class that just ended. You had just spoken a little bit about the trade-offs between forgetting versus learning. Could you speak a little bit more about what some of those trade-offs are, and what are some, and tell us a little bit more about the new open problems that you'd like us to focus on?
Right. I think so for example, if the yellow tigers, there's a bunch of yellow tigers only, and then I say, hey, can you unlearn some of the yellow tigers? So in the extreme case, think of it as just one image repeated 10,000 times, and I say I choose a subset of the same. It's the same image, but I say forget these 100 and remember those 9,900. But it's the same image, so it's not possible. So either you will entirely forget all 10,000 images, or you will only remember all of them because it's the exact image. So that sort of entanglement, how well that can be done, let's say it's yellow tigers and white tigers. Maybe you can say forget all the white tigers, and then in those over parameterized settings, I can try to quote unquote embed those smaller subclasses into pockets of over parameterized loss landscape in such a way that I can easily forget them, because it can be done that way. But if their features are almost exactly the same, then no matter how much over parameterization you have, you cannot make them far apart in those embedding spaces. So then with that, are there fundamental trade-offs that we can study, like under these distributional assumptions on the data, how much you can definitely not unlearn beyond a certain point, right? In context of privacy, for example, it's similar, right? So if, for example, there is privacy leakage because of membership inference attack, if there are many such cases, then it becomes indistinguishable. So how do we ensure that we are, if there are rarer examples, right, and if those rarer examples are doing better by using certain algorithms. So in general, right now, if you read papers out there, it's just SAM is great, just use wider minima. But I'm saying there is this, like, it's not a free lunch. You pay more because there's privacy leakage. So can we design algorithms which retain the generalization performance of SAM while also ensuring that the privacy leakage is minimized? And again, the same unlearning question there. Under what conditions is it actually, what is the limit of this trade-off? So, if there are error classes and I want the model to be private, maybe I cannot do better than a certain amount on those rare classes, because if I try to do that, there will be privacy leakage. I cannot arbitrarily align the two subclasses so much, because then it will be indistinguishable. Then it will not, everything is just going to be. So, can I, for example, design algorithms that scrub out the whiteness of white tiger and yellowness of yellow tiger and focus on other parts which are common features, but how do I find out what to scrub out? Is that something that is maybe a human in the loop setting, where we say that these features should not, you can rely on too much, or implicitly can you design algorithms that causes this varied alignment within white tigers and within yellow tigers, but less alignment across the two? So, can we design algorithms? So, that was the last slide, where we want to align not just white tigers amongst themselves, yellow tigers amongst themselves, but they together align more while focusing on more common features, so that effectively you are scrubbing out the yellowness and the whiteness. So, those are the kind of questions that I think will give us better trade-off in terms of better generalization performance, but not too bad privacy and vice versa. So, how do we seek better on that spectrum of trade-off of generalization and accuracy, and privacy leakage? How do we seek like better vantage points that, like, obviously there will be limits, but how do we theoretically define those limits, and then how do we try to seek those?
Right. So it's more like trying to find the commonalities between them instead of scrubbing out the quirks that make them indistinguishable, like 100 versus 900 example.
Right, exactly. Yeah, so the question was, is if there are two similar, then we cannot do anything, right? If you are scrubbing out, if you are removing impact of certain data points, you will have to forget everything. If there are 10,000 images of the same thing, you cannot forget 100 of them, right? As opposed to that, the goal would be how do we find commonalities and build models on top of that, right? Instead of like, but then again, there could be cases where those sort of eccentricities are important to generalize, right? And there's a paper by, I think there was a talk earlier this year by Gavin Brown, that one of the colloquial talks, that talks about there are limits to this. So, you cannot just say that I'm going to just learn everything and not pay anything in terms of privacy leakage. So, those idiosyncrasies in the data sets have to be captured if you want to generalize on unseen data points, right? Because effectively you don't know in what direction your unseen data point might go in. So, if you don't know that, you will do structured memorization on everything available in the training data, and then that would lead to privacy leakage. Does that answer the question? Yeah.
Okay, so yeah, let me ask a very interesting observation. So my question was regarding privacy leakage part. So there, I can see the how you are able to relate that to the mutual information, and then are there already measures available or techniques available so that you know that this much is the leakage with the current model, and maybe your hope is there to reduce the mutual information as much as you can by adding possibly more data into it. So what are the current practices to deal with this privacy leakage regarding the membership inference part?
So I'm aware of like these differential privacy sort of techniques, which is not explicitly designed for membership inference attacks, but in general, basically you don't learn the specific idiosyncrasy in the data. You try to scrub that out by adding some noise. You say, I'm not going to learn this exact data point. I'm going to try to scrub out or add a random noise a little bit, perturb it a little bit. You perturb essentially the gradient a little bit, but then there you pay quite a bit. If you look at DP-SGD, you pay quite a bit in terms of generalization performance. And then there are variants of which try to seek like better trade-off in terms of generalization accuracy and this. My hope is that this framework of linear stability and alignment does that without those perturbations. So instead of just scrubbing it out by adding noise, can we focus on aligning these, like regularizing the cost function in such a way so that the largest eigenvalue, or in general the spectrum of the Hessian gram matrix that are defined is more favorable, that would lead to less privacy leakage because the alignment is more. So that is what we are focusing on right now. As far as I know, that alignment angle specifically for privacy stuff has not been explored. That's as far as I know. But yeah.
Thanks. Are there more questions? I also can't see more question, and we are also out of time already.
Yeah.
So I guess let's thank the speaker again for
Thank you.
talk.